Okay, so we are given that we have this function g of x, and we're defining the function g of x as being g of x equals x squared. Another way to write x squared could be that x squared equals the antiderivative or the integral of 2x dx. And I'm just doing that just because. And I am being a little bit loose with the plus c's right now, I realize that, but it's kind of to make the point. So we're defining g of x equals x squared as a function. We're also just noticing that you could rewrite x squared as the integral of 2x. And so what we're going to write is g of x can be defined by an integral. We can use substitution. And I'm going to write just another reminder, g of x equals x squared, and you could say the same exact g of x could equal the integral of 2x dx. If we wanted to get a derivative, so if we wanted to get g prime of x, we know from looking here that the derivative has to be 2x. Right? Maybe I'll write it here so it's a little clearer. So g of x equals x squared clearly has a derivative of 2x. But since these are the exact same function, if x squared has a derivative of 2x, then the integral also has a derivative of 2x. And that's probably one of the big takeaways from this lesson. And so we're going to actually just write that again in a little bit of a table. Here's what we already know. And here is what is also true. And we're just kind of going through this again. We already know g of x equals x squared, so g prime of x equals 2x. And since we agreed that this integral of 2x dx is actually the same thing as x squared with a little bit of looseness for the plus c, then we can just summarize that it must have the same derivative. Okay, we have one more step on this to go. The way an integral defined function looks is that it looks like a function built from an integral. So we have this, there's kind of a little new part to this. Again, we're talking about g of x equals x squared. And then let's look at its counterpart. So let's say that we had the integral from 0 to 1 of 2x dx. And let's think about what that would look like. The function 2x is going to be a line, right? This would equal the integral of x squared, right? The antiderivative from 1 to 0. And what's the answer to that? 1, right? Because it would be 1 to the power of 2 minus 0 to the power of 2. So that equals 1. And what that tells us is this area, this is area, under the function 2x. So far, so good? We already knew that, yeah? Let's do one more. Let's say that we have an integral from 0 to 4 of 2x dx. And I'll let you go ahead and figure that out using the other part of the fundamental theorem, where you take the antiderivative and plug in. And we got 16, right? So that means that this area inside of here is 16. And so what integral defined functions are good for is looking at how this area grows, right? So if I just keep changing this upper number, then what basically happens is, and I have this on Desmos, but I'm not going to play it just yet. What basically happens is we see the area growing and growing and growing and growing. So somebody said, you know what would be really easy is instead of defining g of x equals x squared, because by the way, these numbers are actually giving us that graph of the antiderivative. So let me show you this really quick. We didn't do 0, but do you agree it would be 0, 0? Then when x is 1, we got an answer of 1. When x was 4, we got an answer of 16. If x were 5, if the top number of the integral were 5, then we would get 25. So basically, we're drawing a parabola here, right? So the answers to these integrals are getting us the graph of the x squared. So what somebody says is, hey, since all these answers basically they measure area and they create the graph of x squared, instead of saying g of x equals x squared and having to get these little numbers one at a time, let's define g of x this way. G of x can equal the integral from 0 to any number of 2x dx. So g of x could equal the integral from 0 to 1, or from 0 to 4, or from 0 to 5, whatever we choose to plug in here. But we can't do it just like this. There are too many x's. This x is the input for g of x. This x has to do with area. So here's what they do. They change it, and they change the variable on the second part of it. 0 to x, and usually they change it to t's. 2t dt. It's the exact same thing. It's just they didn't want both things to be defined by x's. Because this variable switch is the way it's always done, it makes the next part of our life a tiny bit harder. But it's good to know that the only reason these are t's and these are x's is because in calculus and in math, there comes a time where these variables do need to be different. For us right now, honestly, if they stayed the same, we could make it work. We'd get a little confused, but we could make it work. But they have to change it, which leads us to have to be prepared to do some other things. So this is now a function, right? This function says whatever answers you get from this integral, those answers are this function g of x. And because we know earlier, we talked about it earlier, this derivative g prime of x, we already know that this basically becomes x squared, right? Do you agree with me? So this derivative has to be 2x. And you'll notice the t kind of changes back into an x. So in an integral defined function, the derivative of the function is the integrand with the function's variable. And what happens to kids with this is it's almost too easy. They're like, that's all there is to it. So if I were to give you this function and I said, hey, here's g of x, please find the derivative. The answer is literally 2x. You take the integrand and you just replace the t variable with an x, and that's your derivative. Okay, so I call this the like you just have to be a believer, okay? Like that's literally the point of today's lesson, and some of this other stuff I showed you is because we're going to need it for future lessons, okay? So let's do some examples. Let me turn my page so I have the right examples. Okay, here's what the fundamental theorem says for integral defined functions. So the FTC says, and it says just what we just said, if g of x equals the integral from 0 to x of 2t dt, that g prime of x, there's a reason I'm writing this again, equals 2x. Let's generalize it. Here's the way it shows up on the AP exam usually. It still uses g of x, and it gives you an integral from, let's just say, 0 to x, and then instead of giving you a real function, they just put in f of t, meaning any function. So over here, I'm writing like the generic version. And by this way, the 0 here can be any number. This 0 can be any number they want, and it doesn't change what we're doing. And so g prime of x in this situation equals f of x. So we change f of t to f of x, and that's it. So here are some examples. You're going to like this because it's straightforward. And the things that when we raise it up a level, it still stays pretty straightforward. So let's say you're given g of x is an integral defined function from 9 to x. That's an x on top, sorry. And let's say the integrand, the inside, is sine t dt. And you're asked to find g prime of x. Please write the answer. You have to be a believer that the theorem is true. There are going to be doubters among us. There are going to be people who aren't sure if it's true, who don't fully believe in this fundamental theorem. I will take a volunteer who's a believer and understands the theorem. Miranda, you look like a believer. Yes, your faith is a little on shaky ground, but I could hear it, that you are discovering the truth of the fundamental theorem. Yes, it feels too good to be true. Here we go. Let's try another one. Let's reinforce our belief. Oh, okay. Look, I know the force is strong in this room. So I decided that because the force was strong, I was going to go from like just a little one term example to the big mama. Here we go. Yeah, this function is like not messing around. It starts at negative pi. We ain't kidding. Is that a number, by the way? Yeah, it's not a variable, it's a number. And it has natural log of t minus 8t squared. Wait, plus cos of 5t dt. And I want you to find g prime of x. And this is a real test of faith. This is like walking on hot coals. If you just believe and you just do as the guru had shown you, not me, by the way, the hot coal guru showed you, then you will get to the answer. It's all about believing. You don't even need the force, just to believe. I feel like Daniel looks like he's a believer. Daniel, show us that you have faith in the fundamental theorem of calculus. Very good. Wow. Yes. Hallelujah. Yes. Yes, that is it. Woo! That is a fundamental theorem, y'all. That is a fundamental theorem. Now, okay, I'm going to admit that as you go up the chain of belief, and like if you were in Scientology, I'm sure you'd be in the inner ring by now, you find out that there are a few situations where your faith might be tested, but if you know the chain rule, you're going to be okay. So, the chain rule only applies if your x bound has a derivative that's not 1. Okay, so somebody got all fancy here and they're like, oh, instead of going from -3 to x, we're going to go from -3 to x to the 5th. Okay, it's sort of ridiculous. It's over the top, but it is a good time to show that we believe and to show that we also have studied the order of the chain rule. So the rule here is you substitute this thing as usual, and then you put everything in parentheses and multiply by the derivative of this. Okay, so here we go. G prime of x. We're going to put that x to the 5 where the t was. No problem, right? So far, so good? But because x to the power 5 has a derivative, we're just going to throw all this in parentheses, and we're going to do the derivative of x to the power of 5. That's it. And you don't even have to simplify. Just throw the substituted derivative into a big set of parentheses and just slap your chain rule there. Okay, here we go. Let's do another one. This one is for those of the highest faith. If you are a prophet of the fundamental theorem, this is a plug-in and a chain rule. A chain. That should say a chain. Oh, I literally forgot I was recording. Sorry. Wow. So right away, we know that this is going to end with parentheses 6x squared. Yeah? And then sometimes, though, you have to work it for the substitution a little bit. Big square root sign. It's just meant to scare you. That square root sign, it's just meant to test your faith. Think of it as an opportunity to show your knowledge of the FTC. So I still keep my root sign. And since it's t squared, when I put in 2x to the power 3, I'm going to need to square 2x to the power 3 because the t had a square on it. Does that make sense? And then just minus 2x to the power 3 because the other one was just a plain old t. And then big parentheses outside, right? Not even inside the square root. We're going to chain rule this. That's a 3. We have one more example, but before we have it, what questions do you have especially about the last two? You can ask me or you can ask your table. If I were to give you a quiz right now, what would you have wished I clarified? Amber, do you have a thought? Correct. Yes. No matter how many variables you have, you're just doing the chain rule once. And technically, we're always doing the chain rule. It's just the derivative of x is 1. So no one bothers putting a times 1 at the end of that. So yeah, just one time. Yeah, that's a great question. And to be clear, too, you're taking the derivative of what was the upper bound. What else could I clarify that might give you a hiccup? Okay, last example. I'm going to call this one, they got creative. Okay, this is when the authors of tests and things just try some funny business on you. So here we are getting creative. And the function they gave us was g of x. And this time, they start it with x to the power of 5. So that looks like a regular function for a minute. But then they're like, oh, okay, I'm going to change that to a plus. All right. They're like, oh, just kidding. It's a regular function and it has 0 to x of 10. That's tan t dt. Would you be brave with your newfound faith and just do what your heart tells you? Use your faith and your knowledge and see if you are following the right path to derivative nirvana. Isabella, what does your faith tell you? So close. So close. This is not inside the integral. So what do you think we should do with it? Which is? There you go. That's it. So we only apply the theorem to the thing. We only apply the theorem inside the integral. Outside the integral, the rules of derivatives work as usual. Are we feeling faithful? Okay.